So the next major topic we have to discuss is stress concentration. Okay, so we all know what is stress concentration. All the machineries, the working machinery would have some point at which the stress is concentrated, and it can be due to many factors like improper design. Um, okay, you are not designing based in engineering, following the engineering principle, and in many point can act as a stress concentrator and eventually cause the failure of the machine. Okay, so we already discussed the formula of whether various cross section for tensile forces, compressive forces, bending, torsional. We have discussed all in the previous question, previous video, previous theory. But what we have discussed is all uniform cross section members. Okay, there is nothing of a step one. Everything we have discussed of a cantilever beam, whatever we have discussed is all an uniform member, right? From left to right, from start to end. It's of uniform diameter, uniform length. Okay, so that's not the actual case. We know in real life, all the machinery wouldn't be having the same. Suppose even one part of a machine won't have the same sized rod, right? Same diameter rod would vary. So there would be a step for varying diameter based on its working principle, based on its function. So in actual practice, it is difficult to design a machine without permitting some change in the cross-sectional member, right? For example, the rotating shaft, we know rotation shaft, right? So there are different diameter in it, right? Rotation shaft has step to different diameter to accommodate gears bearing fully. Okay. So they have to be in different diameter, not to in contact with the different shape or different diameters of gears. Then the shaft having keyways. Some shaft will be having keyway in order to place in some slot. So it has to be machined. So some shaft has to be machined for securing gears and pulley. So the cross section is changing, or it is not having a uniform cross section. It is changing based on its functions. Okay, so other factors including opening cavities, cracks, grooves, incision, corners, protrusion, sharp edges, or engraving, as well as various surface irregularities such as notches. Okay, we type notches, scratches, marking, or all can occur. Okay, so these are the things you can find in actual case material or numbers. Okay, failure machines uh, and structures always initiate at a site of local stress concentration. Okay, so the failures of machine. Okay, this the machine we're having a failure, right? So this failures of machine structure is due to some point where stress is concentrated, and that stress concentration is caused by the geometrical and the microstructure discontinuous. Okay, we may design in such a way that there will be a point of stress concentration. Okay, we have to keep in mind that whenever there is a point of stress concentration, it will always cause a failure at that point. Okay, that's a general law. Okay, so there's any discontinuity in machine part alter the stress distribution. Okay, there will not be a uniform distribution throughout the body. And the neighborhood of the discontinuity and the elementary stress equation no longer hold. Okay, what you are discussing is a elementary equation, right? Uniform case condition, just axial load, okay, uniformly distributed throughout the length. That's not the actual case. It could vary. Okay, there will be a varying diameter form, varying length form. So the force distribution will not be uniform, right? So that's the actual case. So the discontinuities on a body are called stress risers or notches. The region in which they occur is called area of stress concentration. Okay, the point where actually stress concentrated is called stress risers. Okay, and that area is called area of stress concentration. So these stress concentration or stress risers all lead to local stress mean time higher than the stresses obtained by the elementary equation. Okay, we have already discussed the stresses due to in elementary equation. Suppose there's axial load. Okay, there's a tensile stress is there, compressive stress is there. So we got the value based on the axial load tensile condition. But due to this due to varying diameter, the stress formed in this actual case will be always higher than the stress due to a normal elementary equation. Stress concentration is defined as a localization of higher stresses due to abrupt change in the cross section of the component. This is one of the important point due to the change in cross section of the component. Okay, not uniform cross section due to change in the cross section of components, what it makes to form the what it lead to forming stress concentration. Okay, where high localized where high localized stresses are produced due to the abrupt change in the geometry. It's called stress concentration. Okay. So simple as that, it's due to for mainly formed due to the change in cross section. Okay, won't be happen in member having uniform cross section. Is formed where there is a uneven distribution, stepped or varying diameter, varying length type of members. The stress will not be uniform throughout. The force will not be distributed uniform. So of course there will be a point of stress concentration, which eventually cause the failure. Okay, or stress. So next term regarding the stress concentration is concentration stress concentration factor Kt. So not to consider the effect of the stress concentration. We know that stresses are concentrated on this machine or body. So because we have to find, okay, we have to find how much is the effect or the value of that. So we have to formulate some constant, right? So not to determine the localized stress factor called stress concentration factor. Okay, stress concentration factor Kt. Okay, this is the term we formulating in order to find the stress concentration, which is of the formula Kt is equal to maximum stress by nominal stress. Maximum stress is a maximum possible stress that can be formed. By nominal stress, it's a normal. I mean, the actual stress or we taking from the normal in actual condition, right? Right. For axial load condition, it will be that the normal tensile force, not normal that way, but actual normal force will actual force will be stress will be taken. Like for axial load will be due to tensile or compression stress. In bending, that will be that bending stress. In torsion, that will be torsion stress. That is normal nominal stress means. Okay, the actual stress will be taken in each respective condition. Okay, so KT is a theoretical elastic stress concentration factor for normal stress. Okay, this KT can be only used for case of tension and bending. Okay, it cannot be used for torsional case. This KT, the theoretical elastic stress concentration factor, not simply stress concentration factor KT. It is a theoretical elastic stress concentration factor for normal stress. We know tensional bending are normal stress, right? Now the stress which we are acting perpendicular to the surface of the body is called normal stress. Okay, so tension and bending are normal stress. So this stress concentration factor can be only applied for this tension bending. So Kt, where sigma max is the maximum stress at the notch. Okay, maximum stress that is formed. And sigma is the nominal stress. So we can look at each condition for this equation. So for direct stress, okay, we know what is the direct stress. It could be either no, tensile or compressive stress is called direct stress, right? The one is acting along the axis of the body. So we know the stress equation for direct stress, whether it is tensile or compressive, it is F by A, right? So bending, same equation. We are actually using this equation not to formulate this, right? So for bending, we know the bending stress equation M by Z. We have discussed in the previous problem and theory. It is M by Z. So this stress concentration factor Kt can be no, so can be only applied for direct stress and bending. So in torsional, we form another term called a theoretical elastic stress concentration factor for shear stress. Okay, it is known by Ks. Okay, so for torsion, same equation, same format, tau max equal to tau into Ks. Okay, this tau is a normal equation. Okay, that the equation you use for torsional equation, Tr by J. Okay, and this is section modulus. So this is a normal equation for torsion. So the only difference is Kx is introduced this elastic stress concentration factor for shear stress. So tau max equal to tau Kx. Okay, this is all about stress concentration factor for normal stress and shear stress. Okay, so next is the method of stress reducing. Okay, we have to reduce the stress concentration on various part of a machine. Okay, so the only way to do is to have a better design. You have to design such a way that it would reduce the area of a point of stress concentration. Okay, so number of methods are available to reduce stress concentration in machine parts. Some of them I will be showing that. I will suppose consider this design. This is stepped shaft, right? This is a stepped shaft. This is having this is having a smaller diameter. Then all of a sudden it will increases to a higher diameter compared to this. So like if I design a step in such a way that perpendicularly having sharp corner, these 2 points, this one and this one, will act as a point of stress concentration. Okay, these lines, this parallel line shown is the stress distribution lines. Okay, these parallel lines are stress distribution lines. So as you can see, these are this point, a point of point at which the change in diameter. There is a region of tension, right? The region concentration of stress. Okay, there are more lines concentrated at this point in this region, on both sides of the shaft. So this point will act as a point of stress concentration. So it could cause the failure at this particular point. So it is a bad design. So how to improve this design? By introducing fillet. Okay. See, as you can see, if I introduce fillet, it will be having a gradual, okay, there will be gradual change. Is coming and look at this. It's suddenly not sudden change, it's a gradual change in the change in diameter. So the concentration line or stress lines are going in such a parallel way. So here you can see this sudden change or in perpendicular way with this shaft will be much closer to the stress line, which will be causing a point of stress concentration. But on the other hand, on the fillet radius, will be changing gradually, so it will give a smoother flow of the stress concentration line. So there will not be any point of stress concentration at this part and this part. So this is a preferred design on this design. Okay, so you cannot uh, step a shaft with the sharpy corner. You have to apply filler radius. Next one is using multiple holes in place of a single hole. Okay, we show you that next part. And if the notch is unavailable, it is better to provide a smaller number of smaller notches rather than a long one. But this reduces such concentration to a larger extent. Okay, these two examples I will show you now. So this one is what I just told. We have to increase the number of holes. So suppose we have a design like this. There's a large hole at the center, and okay, there's a large hole in the center, so you can see the sun's concentration line, right? Just come very much close at this point of this hole. There is also one line out down here. So this is the area around this circle. The circular hole will be having too much stress concentration, right? So you can reduce that extent up to an extent by look at this. If I just introduce some two holes along that line along the center line, a number of yeah, just have to increase the number of holes, right? So now you can see the stress concentration line just change gradually. So just change to much larger extent would reduce the area of stress concentration at the center part of this hole. So if I just introduce a number of smaller holes around this or along the same line of this larger hole center, I can reduce the stress concentration up to some extent. On the other hand, using a multiple notch, if I having a path, I can if I cannot avoid notch like this, you know that sometimes these notches are used in metrology lab in order to measure something. So we have to build some part with notches. Okay, this is important. They have to build a part with notch. So if I am just making a part with a single notch on both sides up to the center, you can see the stress concentration line. Okay, it would have so much larger uh, stress concentration at the center part due to the uh, due to much collision of this stress concentration line. So the better design for a notch design is you just have to increase the number of notches. You have to use multiple notches. So the stress concentration line will be diverted like this. Okay, so this is a much preferable design. So suppose if I have to make some part with notch, this is the way to do it. Just increase the number of notches. Okay. So we have two more cases. The use of undercuts. Okay. Suppose I have suppose I have this design. So we already know that the sharp corners in step design is a bad design. Okay, it will cause to concentrating stress. So one solution we have discussed is the use of filler. Okay, filler radius in the place of sharp corners. And the other solution can be by use of undercuts. The undercut simply means that okay, we will be removing some material inwards at that change in diameter point. Okay, look, you can see here, we are just removing at this particular part. Suppose we have this material, we will be removing like the small part on both sides. So it would distribute the stress line in a very uh, proper manner so that it will remove the stress concentration. So use of undercut can be also be improved design uh, for the removal of stress concentration. Then the other hand is the reduced shank diameter for threaded members. Here we have a threaded design. The stress lines are shown on this threaded design. We have threaded cut on this design. So the removing reduce the shank diameter. This is the shank part. Okay, this is the shank part. So just if you just remove the shank diameter to a very less part like this, you can remove. You can see the stress line. It will be in parallel direction. There will not be any point of concentration. So these are the different cases that you can redesign in order to avoid stress concentration.